Okay, welcome to lecture 16 of Submodular Functions Optimization and Applications to Machine Learning. It's May 21st, and we're moving along in the course, and today will be a nice lecture because we will finally get to, in some sense, a particular maybe moment of culmination for this class in the form of the minimum norm point algorithm's proof of correctness, which finally will put to some use some of these tools that we've been defining and gaining some intuition about. Again, reading, I've added a couple of additional readings. So in addition to the ones that we've looked at, you may find Choquet's original 1955 paper on the Choquet integral, which is something that we'll be talking about at the end of today's lecture. This set of papers and actual books on aggregation functions. So it's essentially a set of papers, but there's also a nice book that's worth taking a look at. Of course, Lovász's original 1983 paper, and then Francis Bach has got a nice overview of the Lovász extension that is available for free online. All of these things you can get by web searching them. And then, of course, Tom McCormick's overview of submodular function minimization. Now, I should mention that there are a large number of different algorithms for submodular function minimization, general purpose submodular function minimization. The one that we're going to be reviewing is the minimum norm point algorithm, which is a quadratic programming problem. But many of the algorithms that are mentioned in this paper are combinatorial. They also use the constructs, these fundamental constructs that we've been reviewing, dep and sat and sup, with regard to vectors and associated base polytopes. But we will not have time to go over all of them. A lot of them are fairly detailed and have running times of things like n to the sixth. And anything that has a running time of n to the sixth is itself already going to be a complicated algorithm to analyze. But they're all, most of them are nicely summarized here. And actually, I think he's been updating this paper. So I think it originally came out in 2008, but I think he's updated it since then. Okay, and then of course also you should have read the slides in lecture 14, which are fairly self-contained, but for which there's no official lecture for. Okay, so here we are, lecture 16, the minimum norm point algorithm and the lattice of minimizers of submodular functions and the Lovász extension. By the way, the way you pronounce Lovász is Lovász. I've in the past historically pronounced it incorrectly, but officially it's Lovász with an S, not a Lovász with a sh sound, it's with an S at the end. And that was that's the official Hungarian pronunciation. So if you're interested and if you've learned anything from this class, then you can go around to conferences and walk up to people and say, what about the Lovász extension? And they'll say, wow, this person really knows their submodularity. And that would be a great feat. So in any event, sup, sup, and sat. Actually, there is no sup. It's just sup, sat, and dep. So just to remind ourselves of these definitions, because we will need them presently, the sup is the support of the set. It's basically the non-zero entries. The sat, which is also the same as the closure in the matroid case, it's the maximal tight set, right, which you said is a lattice, but it's also definable as this restriction, this movement restriction property. It's all relative to an x. So we're going to use both of those things. We need both forms, and we actually derived how 16.29 is the same as 16.31. And we will see, we will use them both in both forms. And then similarly, the dep, which is like the generalization of the fundamental circuit, can be seen as the minimal E-containing tight set, right? It's a lattice of E-containing tight sets, and this is the minimal one. It's unique. But it also has a representation in terms of this restriction, movement restriction property. Basically, it's all directions E prime, such that if you want to move in the positive E direction, you have to correspondingly move in the negative E prime direction, right? And we saw that those things are the same. And remember that dep is a subset of sat, and then dep, the arguments for dep E, basically it really only makes sense to take E and sat. So we're really only considering this E here to be one for which E is in sat. That's all we need, and that's all, it really is sort of weirdly defined otherwise. The other thing we have to remember is this critical theorem, which was initially shown by Jack Edmonds, which is the max-min theorem, where basically it says that the maximum here is equal to the minimum here. And the particular form that we're going to take is when we're going to take x, we're going to take the rank of 0, right? This is the rank of 0. We're going to take x as to be 0 vector, and we're taking the maximum component sum where all of the elements of y are non-positive and maximal in the sense of being inside of the polytope. And we're talking about the extended polytope, EP. There's no restriction of PF to be within the positive orthant here. And that's equal to the valuation, that's the value of the minimum of the submodular function. So why can we use this? Why is this useful? Because if we can actually find a feasible vector, feasible on the left-hand side vector, okay? And if we can find a set on the right-hand side, such that, let's say that we can find some vector, let's call it, I don't know what to call it, let's call it z, okay? If we can find a z that's feasible on the one hand, and its component sum is equal to some f of, say, az, right? Then that basically means that az is a minimizer, right? Because of this tightness, right? Because the maximum on the left is equal to the minimum on the right. Therefore, and in fact, that's exactly this is how we're going to use this. This is one of the nice things about strong duality is that you can use strong duality to prove optima, and this is no exception. Okay, so we have different polytopes associated with F. Remember, PF plus, as we were saying, one that's restricted to the positive orthant. PF is there's no restriction, and then the base, which is this thing over here. And then I should ideally also have another picture, but in general, if you were, for example, not necessarily a polymatroidal function, you might actually have the polytope look something more like say this, right, which is the red bit. Okay, if that makes any sense. Let's get this perfect. Okay, perfect polytope. I don't know, but anyway, you get the idea, right? And so in that particular case, the base is this part here. Okay, that just means that the base is not necessarily in the positive orthant also. Right. And so here's the min-max theorem. And what we're doing is we're considering the minimum norm point procedure, which is a quadratic programming. It's quadratic programming. It's not even as general as convex programming, because we've got a quadratic here. This is a quadratic, subject to being in the base. So we're essentially trying to find, going back to this figure, we're trying to find where the minimum norm point is along this base. And so we have some examples of where we said basically these circles are contours associated with the square 2 norm, and then each one of those yellow regions are possible polyhedra associated with the submodular function. And in any case, you get a different minimum norm point. And there's a lot of ways. There's a particular method called the Frank-Wolf method for actually finding this minimum norm point. And I don't think we're going to have time today to go over that. I mean, there's actually a lot of ways of doing quadratic programming. That one actually happens to work particularly fast because it can use the greedy algorithm, Edmonds' greedy algorithm, to find extreme points. Because remember, we said that any extreme point along the base can be found from an ordering of the elements. So you can get extreme points really, really easily. And that's not typically the case for most polytopes, right? Polytopes generally are harder to find extreme points, but within it's a submodular polytope, and when it's a submodular base, we proved all this machinery that said that we can actually get extreme points. Okay.
Question.
Yep.
Is there a reason we've drawn the axes or drawn the polytope in more than negative orthant?
Is there any reason I've drawn what? The polytope?
You've drawn the axes outside the polytope up into the right instead of down to the left.
Well, I think I understand your question. So you're asking why did we not draw this case?
Yeah, exactly.
So remember, this is a good question, and maybe I should talk about it. But if it's the case that the polytope is in one of these cases here, so notice that PF plus, basically all of the structure is in the positive orthant, right, in this case. And so let's zoom in on this one on the left for a minute, upper left, right? So remember we said that that this was like, let's call this axis E1 and, whoops, O1. Let's call this axis, say, E1, and this axis E2. Okay? And so we said that this point was f of E1, and this height was f of E2 given E1, and this height was f of E2. Right, and this point here, oops, that was broken. This is f of E2, and this guy here is f of E1 given E2. Right, this, what I mean by that is that this valuation here is f of E1 given E2, this one down here, and this valuation here is f of E2 given E1. And that's from submodularity, right? So you've got that this guy is less than this guy from submodularity, right? And you've got this guy is less than or equal to this guy from submodularity, right? So now the thing is that when you have a polymatroid function, a monotone, non-decreasing, non-negative submodular function, all of those gains, f of E1, f of E2, and all of these other things, everything's going to be non-negative, right? So that basically means this base is going to live in the positive orthant, right? So getting back to this theorem, you know, when everything lives in the positive orthant, basically the only, we know right away that what the minimum of the submodular function is the empty set, right? And the valuation has 0, since we're assuming that the submodular function is normalized. F of the empty set is equal to 0. And on the right-hand side, the maximum component sum, since the whole polytope, all of the structure essentially lives in the positive orthant, the maximum component sum is going to be the 0 vector. Because getting back to this example here, you know, it has to be, the restriction has to be that it's down in this bit. You can't really see that well, can you? Let's do it over here. The restriction has to be that it's the y less than or equal to 0 means that it has to be down there. And so basically everything becomes dominated by the y vector. And so the y, the optimal y, this becomes y star, which is equal to 0, the 0 vector. And of course y star of E is equal to 0. So in some sense, this example that we drew here is kind of trivial. It's got a trivial minimizer. So the minimizers really only matter when the poly... It becomes more interesting when the polyhedra look like this. And remember, we said that any submodular function, f of a, can be represented as, say, f plus of a, which is a polymatroid function minus m of a, where m of a is a modular function. So really what this means is that if we were to strip out the m of a, I mean, there's obviously lots of m of a's that would work potentially, but if we strip out the m of a and we get back, remember the totally normalized version of the submodular function is a polymatroid function. Each one of those would essentially shift these polyhedra up and to the right, so all of the structure, you know, this is the structure, or this is the structure, all of these structures would be in the positive orthant. By removing that modular component, it would shift everybody up, in which case it's trivially minimized, but it becomes difficult once we add back in the modular subtraction, it becomes hard to minimize, or it's non-trivial. Now it's known that it's polynomial time, and this was a big open question for a long time, is how, if this was an NP-complete problem. It took many years of a lot of smart people thinking about it to prove that this was polynomial time solvable. It's really pushing the boundaries. The reason why it's, I mean, here's one of the reasons why, this is sort of getting into my own, why do I like submodular functions? Because I think, you know, you have problems that are interesting, but oftentimes interesting problems are NP-complete, or worse, exponential time. Submodularity, oftentimes problems involving submodularity are either solvable in polynomial time or approximable, but this is an example of sort of pushing the boundary of what's still solvable in polynomial time. It's still a very interesting, hard problem, but still somehow it's oftentimes doable. And often we care about polynomial time, especially we care about lower order polynomial time, because oftentimes applications, you know, need that. Exponential algorithms become difficult. Okay, so everybody, does that answer your question? Okay, so let's say that, so we've got this optimization problem here, right? And let's just name the optimum solution. Let's say that x star is the optimum. It's unique, right? It's the unique optimal solution. It's called the minimum norm point. And it's unique because it's strictly convex problem, right? So it's a quadratic, right, which doesn't have any discontinuities. So it's a quadratic minimization subject to a convex polytope constraint. So it's got a unique minimum. And let's say that x is the unique minimum, and it's the optimum. And define a couple of different vectors. Let's define y, which is going to be the non-positive elements of x. So every time x is positive, we're just going to set it to 0. So y is another vector, but we're just taking, remember the symbol is the meet of x star and 0. So basically we're just, any positive element we're just setting to 0. The negative elements we're staying put. And then a minus is going to be all of the all of the elements that have negative valuation in x star. And then a0 are all of the elements that have non-positive evaluation in a star. So we should see right away that, therefore, we have that, x star evaluated at a minus is the same as x star evaluated at a naught. Why? Because all of the elements in a naught, not in a minus, have 0, which is also equal to y star evaluated at a minus, because y star has got all of the positive guys stripped away, which is the same as y star evaluated at a naught, again because of the 0 valuation. So we have that. We also, of course, have that a minus is a subset or equal to a naught, right? That should be clear. So we're just defining these quantities. Everybody got what they are? Now it turns out that these quantities solve the submodular function minimization problem, strangely enough. So it means that you find the minimum norm point. I'm going back to here. You find the minimum norm point here, like this guy. If this is the polytope here, and this is the minimum norm point. So we have two coordinates. This negative one, this positive one, and this negative one. Let's say that this is E1 and E2. So I guess they're both negative, aren't they? So let's see. Is there one where it's here's one where I think one of them is positive. So this one, this is E1 and E2. All right. So here are the coordinates. So E2 is positive and E1 is negative. So therefore, f of E1 is less than or equal to f of A for all of A. Okay. So E1 becomes the minimum. Because that's basically what we're going to see. Okay. And then the proof of this, like I said, so basically this means we just need to solve the quadratic programming problem, but we want to prove why this is true. And the proof, I think, really sort of nicely uses dep and sat that I think we should have a lot of intuition about now. Okay, so what the theorem is saying is that, let's say that y star and a minus and a naught are given. So we've got this guy, right? And the theorem states that y star is the maximizer of the left-hand side of that min-max inequality. Remember the min-max inequality? Just, whoops, you don't want that. It's the inequality that basically says the maximum y of E subject to y less than or equal to 0 and y in the polytope. So that's the max side. And then the min side is the minimum of the submodular function. So equation 15.12 is the corresponding equation in last lecture. But it was repeated again in the review section here in this lecture. And so anyway, it's basically saying that y star is the minimizer of that, is the maximizer of that. And also, a naught is the unique minimal minimizer of the submodular function, and a minus is the unique minimal minimizer of the submodular function, and a naught is the unique maximal minimizer. And so what this really means is that in this lattice of minimizers, so here's this lattice, we've got a minus being the unique minimal minimizer, and a naught being the unique maximal minimizer. This is the sublattice of 2 to the v corresponding to the minimizers of the submodular function. Right. And remember we showed that all minimizers of the submodular function are closed in a union and intersection, and so therefore they form a lattice. And that's the other thing we mentioned about how lattices are kind of like the discrete equivalent of convex sets. Right? Convex sets of convex sets. Okay. Okay, so how do we prove this? Does everybody get this statement of the theorem? Okay, so first of all, it's the minimum norm point, right? So x is therefore it's in the base, right? Because x is feasible, and so that means that x of e, the component sum, is equal to f of e, right? Because it's in the base. Any point in the base has to have that property, x of e. So that basically means that sat of x star, the maximal tight set, is equal to e, right? Because everything is tight. When if you're in a point in the base, everything is tight. So that e is sat, and so that means that we're free to choose any lowercase e in depth. So at x star, the minimum norm point, we're free to choose any e in here. Now consider any pair e comma e prime. And we're going to choose an e and a minus. So a minus is this, are the negative elements, correspond to the negative elements of x star, right? And then choose any e prime in the depth of x star e and e, okay? So then first of all, we have that x star of e is negative, right? Because we chose e to be an a minus, right? And also because e star we chose to be in depth, it basically means that there exists some strictly positive alpha such that we can move in the positive e direction and negative in the e prime direction. And it's strictly positive, so we can actually achieve movement. So we might be, it might be a vertex, who knows where it is, but its point is that we can move in those two, in that direction, in that, in some sense, negative 45-degree direction along those two axes. Okay, by the definition of depth, right? So already we've used both definitions of depth, right? Now we do also have that x star is not only feasible, but it's minimal in the L2 sense, and it's the unique minimum element, right? Because it's a quadratic, it's strictly convex everywhere. And we also, what we're going to claim is that, by the definition of depth, we also have that when we adjust x star in this way, when we nudge a little bit in the e direction and a little bit in the e minus direction, thanks to the definition of depth here, we haven't left the polytope, right? And in fact, not only that, but we're still tight. And the reason why we're still tight is because when we take the component sum of this vector x star that's been nudged a little bit, that's just equal to x star of e plus minus alpha, which is still equal to f of e. So what this means is that, think of this as like this new nudged vector. Let me color it in like red or something. So here's the new nudged vector, right? So the new nudged vector, the red vector, right, it's just one vector. It's moved a little bit in e direction, a little bit minus in the e prime direction, component sum on e. So that guy, this nudged vector here, again in red, since it has valuation f of e, it's still in the base polytope, right? So it's still in this base here. Everybody see that? So let's then sort of define the elements of these new nudged vectors. So here are the old elements, the ones that haven't been adjusted. And let's call this guy x star new e and then x star new e prime, right? So x star new e is basically x star e with a little bit of extra alpha, and x star new e prime is x star e with a little bit less alpha, which is still e tight. Now, because x star is minimal in the L2 sense, we're basically taking the sum of the squared elements, right? So all of the elements that are the same, namely all of these guys, don't change, right? They haven't changed, and we're taking the sum of the squared elements. So it must be the case that when we nudge x, when we go from x to this new vector x guy here, it must be the case that we're no longer the minimum, right? Because there's a unique minimum, and we've moved it alpha is strictly positive, and we moved it a little bit. So therefore, the only way that loss of minimality could occur is by the two component sums of the new element, of the new vector, which are these guys, have to be strictly greater than the two component sums of the old ones that before they've been adjusted. Right, again, it's alpha is strictly greater than 0. That's the definition of dep. Okay? So that's using the optimality of x. Now we're going to use this optimality property to prove something about the valuation of x star e prime, the original x star e prime. So we had that we chose e to be an a minus, right? Which basically said that x star e was negative, strictly negative, because it was chosen from the a minus. And we're going to prove that x star e prime also has to be strictly negative. And the reason why is because if x star e prime is greater than 0, then it's possible that we could have this guy being strictly less than this. The reason why is because, we said that, let me just choose the right colors. We said that this guy is less than 0, right? We're adding a positive value, so it's going to make this whole term here, make it a little bit smaller. If this guy was greater than 0, we're subtracting a positive value, so it would make this guy a little bit less. And so these two guys are going to be less than these corresponding guys, which would violate the optimality, which contradict the optimality. So it means that thus x star e prime has to be less than or equal to 0. Okay? But we're actually going to say something stronger, which is that x star e prime is actually strictly less than 0, because if it was the case that x star e prime was exactly equal to 0, we would have a similar contradiction. Namely, we would have this. Right? And that basically would, again, contradict the optimality. And so I'm going to leave this as an exercise for you to show why this holds. Okay? This is a great way of adding problem sets. It's just like some fact in the middle of a proof, which forces everybody to read the proof, right? So, okay, so then, therefore, we must have that e prime, x star of e prime is strictly negative. Okay? Okay, so now what this means is, sorry. Yep. Sorry, you can say again?
The second bullet point again, how that inequality come into picture.
This second bullet point here? Because x star is optimal, right? Is in the L2 sense, right? It's a unique optimum, right? We're taking two elements and we're adjusting them like one of them's going up and one of them's going down, right? This guy's going up, this guy's going down. We've done real work, right? Alpha is strictly positive. It means that we must have made the vector no longer optimum. And it's optimum in the sense of it's no longer minimum, right? So anything new would be this. And remember, most of the elements are the same except for these two elements. We've only adjusted the two elements of the vector. And so it must be the case that when you subtract one from the other, all of the elements except for these two are different. So it must be the case that these two on the right are summed together are strictly greater than these two on the left, which are the original elements in the optimal vector. Okay, so then what this means is we chose any arbitrary e in a minus, right? We chose any arbitrary e, and we chose any arbitrary e prime in dep. And then we've chosen for these any arbitrary pair of elements, or arbitrary with these restrictions, we've shown that x of e prime is strictly negative, which must mean also that e prime is also in a minus, right? Because a minus are all of the negative elements. So what this means, therefore, is that for any e in a minus, we have that the dep of x star e is in a minus. Because every single element in dep for that given e is in a minus, so therefore all of the dep is a subset of a minus. But then, by the way, so a very similar argument can show, maybe I should make this as an exercise, that if you take e in a naught, then dep is a subset equal to a naught. Remember, a naught is a minus plus the 0 elements, the elements that have 0 valuation according to x star. Okay? But the thing to think about right now is, the one we proved is this one. Okay, so that therefore means that if you union together, maybe this should have been a bigger bullet point, that if you union together all of the depths, we're going to exactly equal a minus. And that might take a little bit of thinking, but essentially what we're saying is that for all e in a minus, dep x star e is a subset of a minus, and also, e is in the dep x star e, right? So therefore that implies that if you take the union for all e in a minus of dep x star e, that has to equal a minus. Since a minus can't have any other element. Since if it did, we just take its dep, union it together, which is a subset of a minus. So therefore, it means that these depths are sort of a cover for a minus, and similarly, there's the exactly analogous property for a naught. Does everybody see that? So we have this is a cover for a naught, and we have that this is a cover for a, the first thing is a cover for a minus, the second thing is a cover for a naught. The green is cover for a naught, yellow is a color for a naught, a minus. Now get back to the first definition of dep, and we said that, okay, well, dep is the minimal tight set containing E. Right? And what does it mean to be a minimal tight set that's containing E? It's basically saying that this is equal to this, and any subset of dep is no longer going to be tight and also E containing. But then, on the other hand, tight sets are closed under union and intersection, and in particular, tight sets are closed under union. So when we union all these together, all these guys together, unioning all these depths together, we're still going to have a tight set, right? We don't lose tightness by taking a union. And so therefore a minus and a naught are both tight sets. And what does tight set mean? It means, well, that this is really cool, that x star of a minus is equal to f of a minus, and x star of a naught is equal to f of a naught, since both of them are tight. And from just the way that we defined y, remember we have this property. Because basically y of e, we're evaluating y on all of the elements e, but basically y has all of the positive elements have been truncated to 0, or floored to 0. So therefore we can freely evaluate y on all of the other elements. Remember, this is equal to y star of a naught plus y star of e except for a naught. But all of this stuff up here is all equal to 0. Right? So that means we've got equation 16.8. And then we group all these equations together, we have this string of equalities, that they're all the same valuation. So this is exactly what we wanted to do. We found, we need to show that y star is feasible on the left, right? So if we can show that y star is feasible on the left, right, then we found a feasible y star that whose component sum is equal to two sets that we found evaluated with the submodular function, and so and thanks to strong duality, the A's must be optimal. Now, what we haven't yet done is shown y star is feasible. The claim is that it is, and the reason why it is because remember y star is equal to the meet of x and 0, right? And x is chosen to be the base polytope, which is definitely in the polyhedron. y star is the subvector of x, right? Because basically it's either the same value, y star has the same element values as x star, or it's going to be something that's floored to 0 whenever x star has positive elements. And we said that PF is downclosed, right? We know that. That's a property of the submodular polyhedron. And so therefore y star is still a member of the polyhedron. We're good there. Right? On the other hand, for any y in the polyhedron that's strictly non-positive, and if you take any x, which is a subset of E, we have y of E is less than or equal to y of x, which is less than or equal to f of x. So this inequality here is because y. It's because y is in the polyhedron. And this inequality here is because all of the elements in E not in X are going to be negative or 0. So by further adding them, we're just going to make that quantity, the component sum, smaller. Right? It's because we're assuming this property. So what this means then is that we found a feasible vector y star, that it's, dominated by 0. It's in this guy, and this is true for all of x, right? So that means that we've got this quantity. Y star of E is upper bounded by the minimum of the submodular function. This is by that duality thing, right? Right? Everybody see that? So what does this mean? We found sets A naught and A minus that have tightness, that in fact have the valuations exactly equal. So we've achieved tightness in this inequality. So that must mean we've achieved tightness for these sets A naught and A minus and A naught. And since by strong duality, that means that they must be equal. That gives optimality, since everything else can only be non-tight or smaller. So that therefore shows that y star is a maximizer of the left-hand side of the equation, and A naught and A minus are minimizers of the submodular function. Now, the last thing to prove is that the minimal and maximal minimizers. So how do we get that? So we said that A minus is the minimal minimizer. Is any questions about this? Any questions at all? If not, we will move forward. We're claiming that A minus is the minimal minimizer. Or in other words, that any subset of A minus is no longer going to be a minimizer. So let's take something which is a strict subset of A naught. Okay. So then let's consider it, evaluate it at x star. So whatever that x is, right, we know that x star is in the polytope, and so therefore we have this inequality being true, right? Just because that's true for any x. But basically anything which is a subset of A minus, that means that there are going to be negative elements that are no longer counted. And so what that's going to do is that x star evaluated at A minus is going to add those negative elements, and so x star of A minus is going to be strictly less than x star of x. So this is strictly less than this. But then we just prove that this is true. Okay? So any strict subset of A minus has a strictly greater value, right, because of this strict inequality. Okay, so therefore A minus is indeed the smallest minimizer. What about A naught being the maximal minimizer? So for A naught being the maximal minimizer, we need to show that any strict superset of A naught is also strictly smaller. So anything that's bigger than A naught is smaller. So how do we do that? Well, let's take any arbitrary x which is strictly bigger than A naught. So again, we have this inequality. This is the same inequality. Again, it's true for any x. Right? So f of x is greater than or equal to x star of x for any x. this strict inequality comes about, why? Because remember, anything outside of A naught is going to be positive. And so if we're taking X, which is a superset of A naught, we're including elements that are strictly positive, thanks to X, that are not strictly positive when we evaluate the elements in A naught. And so therefore we get this strict inequality here, because we're adding the strictly positive elements here, which are not being added here. But then what we proved a minute ago was just this equality. And so therefore we have f of x, any such x, is strictly greater than f of A naught. And so this follows. And the theorem is proved. So I think that's pretty cool. So I think it's a really sort of neat proof of this theorem. Now it turns out, as we will talk about next time, actually this will be a YouTube lecture, is that you can also prove this by looking at convex duality essentially it's sort of, this is like the dual form, the minimum norm point is like the dual of a convex minimization problem which minimizes the Lovász extension plus a Prox regularizer, which we will see. I will mention this next time. But this one, just historically speaking, this minimum norm point procedure was seen first back in, I think it was originally Fujishige who first realized this and came up with the proof. The proof that we just did is actually an enormously simplified version of the proof that's in Fujishige's book. But this proof is complete. But you can also prove it in this other way by using convex duality, as I said. Yep.
I think I missed something very major over there. We found Y star, we used A naught and A minus, but we never found what X star is. That was array, right? And doing that, find X star, so that minimization.
Well, we don't have an algorithm. We didn't give you an algorithm for computing X star. Like I said, that's an algorithm. We can use any quadratic minimization algorithm we want. I'm saying, suppose we have them, and what we did is we used the property that X is minimum, and we used the property that it's unique. So we did use that. We just said, let's say we're given to it from somewhere. Why is it the case that A minus and A naught are minimizers of the submodular function? So we did use the property.
But we didn't actually...
We didn't compute X star. Right? That's the Frank-Wolf procedure, which does that. Maybe on Monday I'll give you just a very brief overview of that algorithm. I mean, we'll talk about it in a second, but there's a couple of nice pictures I can show you about how it works. I don't have them here in these lectures. But I think what's nice about the proof is that it uses these things. I mean, it's sort of a dual proof, and it uses these constants. It doesn't use convex duality, but it uses sat and dep, and these intuitive properties that we've developed associated with the polymatroid. Right? Just by thinking about these things. So this is what essentially you're asking. So this Frank-Wolf procedure, which is the minimum norm point algorithm, computes X star for you. It's an iterative algorithm. It's a numerical algorithm. Nobody knows how its convergence rate. Nobody knows its running time, however. So it's in practice the fastest algorithm to do general purpose black box minimization of submodular functions. So if you just have an oracle access to a submodular function, in practice this seems to be the best. And it seems to have a running time of anywhere from n to the n cubed to n to the 4.5. I mean, the lower bound, the actual underlying running time of this algorithm is still an open problem. And people have been thinking about it for a long time, but it's very, very hard to solve. Yep.
I can't quite see why it would be hard to find X star. So earlier you said you can find X star just by solving this quadratic programming, minimizing two norms subject to X's in the base polytope. Mm-hmm. It's like, is the base polytope not convex?
No, it's absolutely convex. But remember, there could be an exponential number of vertices. Now, each vertex you can get by, I mean, there's in the general case, we saw this case, like we saw the polytope that had n factorial distinct vertices, and then, like, just square root of cardinality of A has n factorial distinct vertices that constitute that polytope.
So naive algorithm
A naive algorithm could take exponential time. But a smart algorithm that uses Edmonds' greedy procedure apparently, empirically takes this amount of time. And finally, people were, I think people had thought that it might be n cubed, but we've sort of empirically showed that it was worse. It seems to be worse than n cubed. This is the thing I think I mentioned, that when I met Fujishige, I asked him specifically, like, what's your guess? And he said, I hope I'm quoting him right here. He said, I quote, "I hope it's n to the fourth." But he said he wasn't sure. So he's the guy, he's a very nice guy, by the way. Very unbelievably humble for such a smart guy. Okay, so it turns out that with the minimum norm, so we said that there's this whole lattice of minimizers. This is just an immediate corollary that we can show, is that we can very, very easily get any other minimizer of the submodular function. We can get the whole lattice just from the depth function. So if we have these depth functions, that gives us all of the minimizers, again using the minimum norm point. So basically what it says is that, let's say that x is the minimum norm point, which we've gotten from somewhere, and then let's say that a is a minimizer. So if a is a minimizer, then basically a can be represented as the union of a minus, right? Because any minimizer must have a minus in it, right? So a minus is the smallest minimizer in the lattice. And then we just union together a bunch more depths, where dep is equal to, where we're taking a to be equal to am, a to in am, where am is equal to a naught minus a minus. So this basically means that suppose it's the case that a naught subtract a minus is equal to, say, L. Right, so this is saying that there potentially could be 2 to the L distinct minimizers. Right? But it's not saying that all of these minimizers are distinct, but it's saying in the biggest case, in the richest case, if A naught is bigger than A minus by L, then there's going to be 2 to the L possible minimizers. Yep. Question?
So why do you think AM is the subset of A naught minus? Why not AM equal to A naught?
Because that's the statement of the theorem. Because that's what's correct. I mean, we'll prove this theorem in a minute. You're asking why is this theorem correct? I will prove it to you. So, does anyone have any questions about the statement of the theorem? Okay, so let's prove it. I just want to make sure everybody gets the intuition of what the theorem is stating before we actually prove it. Okay, so let's say that A is a minimizer. This is the proof of this theorem. This proof is relatively easy compared to the last one. So if A is a minimizer, it must mean that A is sandwiched between the minimum minimizer and the maximum minimizer. And we also have that y star E is the minimum valuation of f, right? Because that's the same y star that we constructed before. So x is in the polytope, right? And so we have this is true for the particular A. So x star of A is less than or equal to f of A for that particular A, which is the minimizer. And on the other hand, we have that f of A, which is equal to x star of A minus, is less than or equal to x of A. And that's essentially because anything outside of A minus that's smaller than A naught is going to be 0. So if x is a minimizer, this whole thing, all of this stuff has to sum to 0. Each one of those elements is equal to 0. Or in other words, let me just write it this way. So for all E in A naught except for A, we have that x star of E is equal to 0. Okay, so because of that property, because of this, we have that, we still have this nice tightness property, that x star of A is equal to x star of A minus, which is equal to f of A. So A is also tight set for x star. In fact, we have all of these tight sets. Anything in between there is tight. Anything in between this guy's tight. Now, for any A in A, for any In this case, this is clear. For any A and A, basically A is a tight set containing A. So basically, obviously because A is tight, so if we take any lowercase a and uppercase A, then A is going to be a tight set containing lowercase a. And then dep is going to be the minimum tight set containing A. And so therefore we can see that the dep is also a subset of A. This is true of any minimizers. And so we have this same property, that the union of all the deps is equal to A. So that means that A is equal to this bit here, which is the union of all A and A minus, the union of all A and AM. There's some AM, which is equal to the difference between A and A minus, such that we can represent A in this way, which is then is equal to A minus using this bit here. Okay. And so that basically shows it. It's this right-hand side. So now that does not mean that all, 2 to the L, essentially elements A between A minus and A naught are minimizers. It has to be writable in this fashion. So it has to be these unions of these deps. So you can't just trivially take the Boolean lattice. You have to do it via these deps. So it's an exercise to come up with a counterexample where if it's within the sandwich but not representable in terms of these depths, it's no longer a minimizer. Right? In the statement of the theorem, we assumed that it was a minimizer and we said it can be represented in this way. And that any minimizer can be represented in this way. Now, it's easy to actually, if we have depth queries, we can actually construct any minimizer. Right? We can just go ahead and then take A naught minus A minus, and then just union together these depths and get all these minimizers. It might be the case that they coincide. Some of them coincide with each other. But that's fine. We just take set union and we get this lattice of minimizers from that. The cost of that procedure would be 2 to the L. Okay, so let's talk a little bit more about this. So if it's the case that the gains are strictly positive everywhere, so remember, if you have a set A, and every time you add an element to the A, it gets strictly greater, then can there be more than one minimizer? No, there can only be one. So that basically means that if that's true, if this property in yellow is true, then it must mean that there's a unique minimizer. That the lattice of minimizers is one element. And one element is closed under union and intersection, right? Just take itself and you union it with itself, and it's the self, and take the itself and you intersect it with itself, and it's itself. So it's a trivial lattice. On the other hand, if it's the case that we just so happen to find that A naught is equal to A, that does not mean that the gains are strictly positive everywhere. Okay, so it's not an if and only if condition. So if it is the case, however, that the minimum and the maximum minimizers are the same, then definitely we have to have that anytime you add something to the maximum minimizer, obviously you're going to get bigger, right? Since that's the maximum minimizer. And anytime you remove something from the minimum minimizer, it has to get smaller. Right? This second thing is sort of a very convenient notation for representing the loss that you get by removing E from a set. Right? And why is that? Does everybody see that? So if we do like F, if we do minus F of, say, E given, say, some set A except for E, that's equal to F of A except for E minus F of A. So it's kind of like the loss. And we're saying that the loss is strictly greater than 0. And that has to be the case if they're the same. Why? Because if you remove anything, they're the same, and if you remove anything, it's got to get bigger. Right? Okay. Any questions? So we now know how to do submodular function minimization, right? Okay. Okay, so I think this is a good time to take a break. So let's take a break and come back in a minute. Okay, so the next thing we're going to talk about is something that's also somewhat fundamental to submodular functions, and that's the relationship between submodularity and convex functions via the Lovász extension. And before we do that, let's just review something from lecture 12, which basically talked about how the greedy algorithm was a defining property for a polymatroid, or in the sense that if we remember, if we take some function f and it's given, and we define a polytope in this particular form, then if we run the greedy solution to this problem, then that's optimal. That's that if it's optimal for all possible w, then f is monotone non-decreasing submodular, namely p is a polymatroid. Remember, we also showed previously that that's equivalent to the definition of p being a polymatroidal polytope. And so remember what the greedy algorithm was. W is given, and the greedy algorithm is the thing where basically we sort decreasing in w, which gives us an ordering of the elements e, and then we define the vector x by taking the differences of the submodular function evaluations in the chain of sets corresponding to this ordering. So we'll review that again, but that should be at this point very, very clear to people about how we define x. And so consider, this is really this optimization problem here, right? Let's just expand that out a little bit. And here's the optimization problem again. Basically, we're given some vector w, and we're optimizing w times x, the dot product, subject to x being the polytope. And we said that the greedy algorithm, again, is something that produces a valuation of x, produces the value x. Now, here what we're doing is essentially saying it's PF, and it's not necessarily the positive orthant restricted version of the polytope, it's the polyhedron. And so we know, therefore, that if we take the axes to look like this, and we take the polytope looks like this or something, if any of the w's are negative, then we can just get an unboundedly big solution by essentially just setting x to be negative infinity, right? Because we can just keep going in that direction, and we'll just get a bigger and bigger valuation of w times x while still being in the polyhedron. So in the polyhedral case, it sort of makes sense to assume that w is in R+, so they're restricting w to be non-negative. Okay, even if it's the case that pf is not restricted to be the positive orthant. Now the greedy algorithm will solve this. The proof that we gave is like borderline almost identical to the case when pf the proof that we gave was that this was the positive version, the polytope version, but the proof of this when w is positive is almost the same. On the other hand, we know from theorem 15.5.2, so remember this is the domination theorem. This basically says that if you are a vector, this theorem says that if you're, do we have this? Yeah, so if you're a vector x in the polyhedron, but you're not in the base, okay, then it's saying that you can take for any x, you can take that there's some y here that's strictly greater than x, where y is in the base. And because of that property, we're increasing the dot product. Junk phone calls. I get junk phone calls these days. So I don't know anyone from Gainesville, Florida. It's like when people call you from Gainesville, Florida, it's definitely someone trying to sell you encyclopedias or something. So I say, well, I have an encyclopedia already. It's called the internet. So we are strictly increasing the dot product, right, by taking something in the base. And so therefore we know that we can get the same valuation, but just by taking w in the base. And because this property is true for any x inside of the polyhedron here, we can essentially, but you know, we know that we can therefore relax W to be positive. So we can just say that W is any real vector, and if W is a real vector and we do this optimization problem, we don't need to say that W is positive anymore. Right? Again, it's because of this domination property of the base. Okay, so the problem we have now is this, right? Or the corresponding version where we restrict it to the base. We can essentially define a function like f tilde of W. So W is sort of the argument to this optimization problem. But think of it as a function. F tilde of W is basically the resulting valuation of this optimization problem, the max of Wx subject to x being in the polytope, or the polyhedron. Okay, so we're just parameterizing this optimization function via W. And we know, moreover, that f tilde can be computed via the greedy algorithm. Right, so the resulting, we define a function f tilde whose valuation is such that we use the greedy algorithm to give the valuation back. It's an algorithmic evaluation. And how do we do that? So we've got this W, and we sort it in decreasing order, and we define the chain of sets so that this is decreasing. And so what is the valuation? The valuation becomes f tilde, right, which is this maximum. This is the optimization problem. But we, from the greedy algorithm, which we proved, showed that basically it's the dot product of W, the resulting W, times the gains, right? These gains here are the greedy order element values of the vector x that solves the optimization problem. But we're just plugging them in, right? Critically, it's important that remember that we're doing everything with respect to this particular ordering. So we're renaming the axes such that E1 is the one for which W is biggest, E2 is the one for which W is next biggest. And if we change W, then the names are going to completely change. So for any particular W, we're going to have to completely resort the elements and rename them, right? But that's okay. We're just naming them in this way for vector convenience. So this is the definition of the gain, right, in equation 16.19. And then we can just write it out in this fashion, where the top element is equal to, well, you can kind of just see this, where if we take the mth element, all of the other ones, so we have like successive i's, like for example, f of ei is going to be the same as f of ei minus 1 when I is 1 bigger than it was. If that makes any sense. And so we can write it in this fashion here. Okay. And so we can then form this chain where the empty set is equal to E will not, and then E, this forms this chain based on W. Okay. So here's the definition again. So if F is submodular, we can write it in this way. And another way of looking at it is just basically a sum of weighted valuations of F evaluated on the sets in the chain order. Right? So this is just basically a very simple evaluation. It's just the sum for I is equal to 1 to m of lambda I of F of ei. And where we're defining, we saw this before in the context of matroids, we're defining lambda m is equal to WEM, and lambda I is equal to these differences. And these differences, these guys here, are all going to be non-negative because we're again sorting E such that that W is descending. Now let's think of this function for a minute. It's like the maximum, it's the max over a bunch of linear functions, right? So this is always going to be convex, right? Because when we maximize a bunch of linear functions, we've got this and this and this and this and that and so on and so forth, and the resulting convex function, or the resulting function, which is the max, is going to be polyhedral convex. Right, so anytime we write a function of the form 16.21, it's going to be convex. And that's even true if it was the case that PF was not a polymatroid. Right? Any function. In fact, any set, the set itself, this guy doesn't even need to be convex for this guy to be a convex function. Right? Because it's just the maximum of a bunch of linear functions. But what we're going to see, however, is that this function here, seen as essentially a set of weighted sums of evaluations, where E is defined according to the sorted order, that may or may not be convex. Right? And that's essentially what Lovász originally demonstrated. So to do this, let's first of all remind ourselves that we can write any vector W as this essentially weighted versions of the indicators. Right? So it's W1 minus W2, which we're calling lambda 1, right? Plus W times the one vector. It's like a characteristic vector of just the one element, plus W2 minus W3, which is we're calling lambda 2, times the characteristic vector of the first two elements, and so on and so forth, all the way up until finally we have one remaining lambda down here, and that's times the all one vector. And moreover, if we're taking the elements so that we're decreasing in W, we have that all of the lambdas are going to be non-negative, except for possibly the last one. And if we take W to be strictly positive, then the lambdas are also going to be positive, or non-negative. Right? So everybody remember about this? This is a review. And we define the sets E based on this decreasing order. So this is this chain of sets, where EI, capital E of I, is just the first I elements of E, of first I elements in this order. It's the order according to W. And so we have essentially these characteristic vectors. One E naught is equal to the all zero vector. One E1 is the vector where you've got 1, 1 and the rest of zeros. And in general, 1 EL is going to be a vector where you've got L zeros here, and L1s there, and N minus L zeros. Everybody see that? It's just basically geometry. And then we also saw, just the previous slide said that we can write W in this way. Basically, W is like a mixture of these characteristic vectors of the sets. So we're in some sense interpolating points. You can think of it as like each one of these characteristic vectors of the set is like a point on the hypercube, because it's a vector of zeros or ones. Any vector of 0 or 1s is a point on the hypercube. This is a particular set of points. It's n points on the hypercube, and it's saying that you can write W as the interpolation of a set of n points on the hypercube, where the vectors lambda are adjusted in this particular way. And the way you get the particular points on the hypercube is by sorting the elements in decreasing order in this way. So, just briefly, like if you have a hypercube, this is point 0, 0, 0, 1, 1, 0, and 1, 1. Right? And let's say that you're a point. Let's say that you're at this point here. Okay, so that means that you're bigger and the first element than the second element. So the points on the hypercube you would choose would be this one, and this one. And you've then therefore defined, in some sense, a region of the hypercube, which is this sort of lower triangular region. And the red point can be seen as an interpolation of the magenta points. And the coefficients correspond to the lambdas. Okay? Now, if we define I guess, so what I'm trying to say is that we've got two different, in some senses, variations of ways of expressing f tilde. One is based on this optimization problem, which is the max of wx subject to x being the polytope. Another which is equal to the sum of this lambda valuations, right? Let's just make sure this is clear. On the one hand, we're defining f tilde of w, which is equal to the max of w transpose x, such that x is in P of f. On the other hand, we're defining f tilde of w, which is equal to the sum or I of lambda I f of e of I. All right, so we have these two different function evaluation definitions. We said that if the function is submodular, then this function is such that it can be represented in this way, where the lambdas are defined based on the greedy algorithm. We do the greedy order, and we define the lambdas to be the difference of these w's. Okay. Now, in general, what we can do is we can, in some sense, define a function in this way even when f is not submodular. Right? In fact, we can do either of these when they're not submodular. Now, the top one we know is always going to be convex. The bottom one, we can define it for any non-submodular function. Right? Now, specifically, how we're defining this bottom one is, again, we're still sorting w, and we're still defining the lambdas according to the differences of the w, and we're still defining a chain E based on the sorted order of w, and we're still accumulating the valuations of f tilde of w in this fashion. Does that necessarily mean it's convex? That's what we want to answer. And then what this slide is intending to ask is, what are the valuations on the points of the hypercube? Because what we can do is we could, for example, evaluate f tilde of w where w is equal to 1 of a for some a. What's that going to equal? And so that's the question we want to try to answer in this slide. And I wasn't clear. I don't think I was clear in this thing. So in order to do that, we take w is equal to 1a, right? And so that means that w is a vertex of the hypercube, right? Everybody see that? So if we just take a characteristic vector, we said this before, in general, if we have a hypercube, here's a nice hypercube, basically every single one of these points here, vertices, is going to be like, 1, 1, 0 or something, right? Okay, so then let's order the elements. We're taking w is equal to 1a for any particular a, and we're ordering the elements in this way. We're in decreasing order. And so that means that once we've renamed the elements, we're going to have this vector w such that the first size of a elements are all going to be 1, and the remaining m minus size of a elements are going to be 0. And moreover, we have that evaluating 1 of a for all I less than or equal to the size of a, we're going to get 1, and everywhere else we're going to get 0. So then when we evaluate f tilde of w, when w is equal to the characteristic vector, we get this, which is the definition according to this form. We just plug in the valuations of the definitions of lambda I, which are these differences. And now we're going to put the vector in, right? Because it's the element of the vector w, which are the 1a. So basically we have this guy here and these differences. So you're going to see that this one here is going to, unless a is equal to the ground set, this one is right away going to be equal to 0, right? So that guy cancels out. Because m is equal to this last element. And in fact, all of these guys are going to be 0. All these differences are going to be 0, because there's going to be 0 minus 0. And all these differences here are going to be 0. The only one that's not going to be 0 is when I is equal to this element, and I minus 1 is equal to this element. And we're going to get 0 minus negative 1, which is 1. Which is 0 minus negative 1, which is 1. And so we just get f of e evaluated at a. But we know what e evaluated at a is, or in other words, the ordering in this chain. We get the size of a position in that chain, which is just equal to A. So therefore, f of w is equal to, f tilde of w is equal to f of A. Okay. Now we've done this only based on the definition of lambdas. Right? So in some sense what we've done is the following. Like we're saying, we've got this hypercube. Okay? We're sort of creating a continuous extension of this hypercube in the sense that we could take any particular point in the interior of the hypercube. Like in 2 dimensions, the hypercube looks like this. So if the extreme points are here, we could take any point in the interior, right? Any w we want in the hypercube. And we interpolate the valuations of the function on the vertices of the hypercube in this fashion. And moreover, on the vertices of the hypercube itself, we still have the same valuations of the discrete set function. Right. So we've created a continuous function, a continuous extension of this function just by this guy lambda. Now does that mean, what does that mean? What do we know about this? So in both cases, going back to this thing, in both cases, like in the uppercase and in the lowercase, where this is the uppercase and this is the lowercase, we have a continuous extension of the discrete set function, right? Because they're both valuations. We know that when f is submodular, the bottom one is equal to the top one. We also know that when the top one is always submodular, we also know that the top one is always convex, and so therefore when the top one is submodular, we know that the bottom one, being the same valuation, also must be convex. So what this means, therefore, is that when f is submodular, the bottom expression is always convex. Okay. Any questions so far? Yep.
In the case of w is equal to 1a, why is f tilde continuous?
It's because w can be any point inside of the hypercube.
But you have fixed it to 1a, there can be only fixed finite number of points. If w is 1a, depending upon...
Yeah, think about it. We're defining a function of w where w is any point inside of the hypercube. So it's a countably infinite number of points in n dimensions.
So for the non-submodular case, it's not restricted to 1a or 1a form.
So I think you're thinking only. This is just one particular example. This is the case saying that if we were to evaluate it at a point on the hypercube, we get back the original valuation at A. So a point at the hypercube. Remember, each of these points at the hypercube corresponds to a characteristic vector, right, of a set. If we evaluate the continuous extension at the characteristic vector of a set, we get back the same valuation of that set. Right? That doesn't mean that if we evaluate it in the interior, we get back the same. I'm just saying that in this example here that I just highlighted in red, we are only looking at a particular vertex of the hypercube, an extreme point of the hypercube. So that's just an example of if we did do it. On the other hand, if we did it somewhere in the middle, it's some strange interpolation of these valuations of set functions based on this chain order, right, that we need to define, that we've defined it based on sorting the elements in decreasing order according to the argument of the function w, which could be any point inside of the hypercube. And that essentially is what we're saying here, is that we can view f defined on the hypercube, right? So here we're talking about the whole hypercube, right? 0, 1 to the e, right? So we're talking about every possible point inside of this cube if we're in 3 dimensions, or in n dimensions it's much bigger, of course, eventually. So let's see if we can summarize this. So we've got that we defined f tilde to be in this way, which is right this sort of interpolation of valuations of e. We have that for any function, if we've defined lambda in this particular way, we have that f tilde of the characteristic vector of A is equal to the original valuation at A. Right? That f doesn't need to be submodular. And moreover, when we have f is submodular, we have that this is true and then this is true. Right? Based on the greedy, and this can be solved by the greedy algorithm. So for any function, even when it's non-submodular, we can actually define it in this fashion. Okay? That's all we're saying. And interestingly enough, I mean, where do the lambdas come from? What the lambdas were like saying, okay, well, W is interpretable based on certain set of points in the extreme points in the hypercube. And so we construct these lambdas, which are the interpolation coefficients of the relevant points in the hypercube, which essentially, when we add them all together, comprise W. And those same interpolation points are the ones that essentially define the valuation of the function. So the lambdas are the same. Right? And then here's the case when we also said that when it is submodular, you get the lambdas in this particular way. Actually, no, this is even when it's not submodular. So this is just how you actually get these valuations. These are the definition of the lambdas based on this fashion. So this is the definition of this form of the function. We know that when it is submodular, this is the same thing, but we don't know if it's the case that if this ends up being convex, if it has to be submodular, and that's essentially what we want to do. So f can be seen as a sum of weighted gain evaluations or a sum of weighted function evaluations. So here's essentially the weighted gain evaluations. Here's the sum of weighted function evaluations. So what Lovász showed, I mean, basically a lot of this stuff, I mean, I always like to claim that, Jack Edmonds showed most of this stuff, I think, in the 1960s. But what Lovász showed in 1983 was that if a function, f tilde of w, defined in equation 6.33, or, basically defined in this way, if such a function defined in this way, where the lambdas are defined based on, decreasing order and all this kind of stuff, as done in this equation, Lovász showed that if a function is defined in this way is convex, then the corresponding f must be submodular. And in such case, therefore, the function, the continuous state extension f tilde, is called the Lovász extension of f. So we're going to assume that f of the empty set equal to 0. Okay. So here's how we prove this. So the theorem we want to state and prove in the next 5 minutes is, and this is actually a fairly nice theorem, it's not too hard to prove, is that a function is submodular if and only if its Lovász extension f tilde is convex. Now, first of all, we can see that when it is submodular, we have that this f tilde is representable as this maximization problem, which we know to be a convex function. So therefore, when the function is submodular, we have the corresponding sum in this form is convex. What we want to show is conversely, if this function, if we define a function in this way, and it happens to be convex, where again the lambdas are defined in that particular procedure, then the corresponding f function has to be convex. Now, first of all, what we're going to do is we're going to use the positive homogeneity of the function. So remember, the lambdas are equal to a difference of w's. So if we multiply all of the w's by alpha, say, that's equivalent when the function is representable in this form by multiplying alpha times f tilde of w. Now, it's only positively homogeneous because basically if alpha is positive, the sorted order is exactly the same. If alpha is negative, it reverses the sorted order. So this doesn't hold when alpha is equal to negative, since we get a completely different set of valuations. But when it's positive, we can do this. So it's called positively homogeneous. And we need the positive homogeneity to show that when this function is convex, the corresponding function is submodular. So we did show already that even when it's not submodular, we have we have the evaluations on the vertices that are already the same. Okay. Now what we're going to do is let's choose any arbitrary a and b, and what we want to show that if we take the characteristics vector of a and b and add them together and evaluate f tilde on the sum of these two vectors, well, that we know just by modularity is equal to this, because we're double counting the intersection. And that we're going to see is equal to the sum of the union and the intersection. So the way we can show this is by defining, let's define C to be equal to the intersection. Okay, and then we have this W vector, and we're going to sort it in decreasing order. And so what's going to happen is when we sort it in decreasing order, all of the elements in C are going to have valuation 2 because they're double counted, right? All of the valuations in the symmetric difference are going to have valuation 1. And all of the elements that are neither in A nor in B are going to have valuation 0. Right? And so you can think of you've got these critical points where all the differences here are going to be all 0. This is going to be 1. The differences here are going to be all 0. The difference is going to be 1, and the differences here are going to be all 0. So there are only, in some sense, 2 critical points when this vector changes. So now when we consider this function here, right, we have lambda c is equal to 1, because that's going to be that first critical point. We're going to have lambda a union b is equal to 1, and the rest of the lambdas are going to be equal to 0. So what we're going to get back then is that because it's only the critical points that matter, that f tilde of w is equal to f of the union plus f of the intersection. Okay, now f tilde is convex by assumption, and what we want to do is use the convexity of f tilde to prove that the function is submodular. So f is convex, and we saw that it's positively homogeneous. And so again, let's take any a and b and evaluate the average of these two functions. That is just equal to the average of the f tilde, is equal to half of f tilde evaluated at the sum of the vectors, which we just showed, right? Which, thanks to the positive homogeneity, is such that we can actually bring the 1/2 inside, right? Which, thanks to the convexity, satisfies this inequality, which again is tight. Basically we have at all of the hypercube, at all of the vertices of the hypercube, we have exactly the same valuation, right? So we get that this is equal to f of a plus f of b. So when we essentially cancel out the 1/2, we get back the submodular inequality. So it's interesting that, where does the convexity come about? I mean, like you might think, well, how does, we've been talking about how submodularity and concavity essentially correspond to each other this whole time. And even this inequality, we said this is like the submodular concave definition, because when we think of it as a second derivative, it's saying that it's negative. But here we're saying that this actually also sort of corresponds to a convexity kind of thing. And the convexity corresponds to this inequality here, right? So that convexity inequality followed by this equality based on, properties of this weird function means that it's identical to submodularity of the original set function. So therefore f must be submodular. So this was sort of remarkable when it was first shown, like in the late 70s, I guess. And so I think that we really sort of deserve to give credit to the people who sort of discovered this stuff. First of all, Jack Edmonds. This is essentially his paper in 1969 that basically outlined a lot of the things like the greedy procedure, the min-max duality theorem, and all of these things that we're using that actually has led to the fact that submodular function minimization is polynomial time. And then Lovász, and this is his paper from 1983, where he sort of first shows and mentions that the Lovász, this thing which people now call the Lovász extension, is convex if and only if the function is submodular. And this then was used to show polynomial time minimization is possible for submodular functions using the ellipsoidal procedure. That's not a practical procedure, but basically showed it's possible. Or in other words, you can get the minimum of the submodular function based on convex minimization. And next time we'll talk a little bit next time about primal solutions to submodular function minimization via the Lovász extension. That if you just do, you can just do submodular function minimization and you get a solution, and that even though the solution you get might not be a vertex, you can very, very quickly get a particular point. You can take that solution which is not a vertex and quickly get a whole chain of minimizers from that. Okay, are there any questions? So like I said, next time I see you, it will be YouTube only. Or actually, you will hear and see the slides. You won't see me. But please do watch the lecture before Wednesday. And I will see you soon.